Okay, let's get started. Everybody, can you see my screen?
Yes, sir.
Okay. Um, so you see that last time we were discussing about magnetically coupled circuits. So today we will continue that. Um, at the beginning, there is a problem. You see, determine the voltage V naught in the circuit of the following figure. So if you see the circuit, this is magnetically coupled circuits. Here is that V naught. So you have to calculate the V naught across 10 ohm resistor. So this means that if you can find out this I2 current that is indicated, then that current multiplied by 10, that will give you the V naught. That you have to do. So now here there is a voltage source and this is 4 ohm J8. So these are already given in phasor domain or frequency domain. So you are fine. And this is the mutual inductance, J1 ohm, although this is called the mutual reactance because it is given in terms of ohm. And then this is J5 and this is 10. And these are the dotted point. Here is the dot and here is the dot. And this is the given direction for ion.
Yeah.
So, sorry?
With the dots in that configuration, do you add J1 or do you subtract J1 when the dots are opposite?
So these dot were given in the problem. These dots are given in the problem.
Right. So since they're opposite, you want to add that induction J1.
Yes, exactly. So yeah, you're right. So therefore, for example, for ion, you look, so because this is clockwise, so it will enter at the dotted terminal first. And then in this case also, you see, because this is also clockwise, I2 direction, that is also entering at the dotted terminal. So that's why they will be, the mutual inductance will be added, the voltage corresponding to mutual inductance. So you are right. But for example, if this dot would be here, just an example, then that would be subtracted, the mutual voltage. Because if this dot would be here, then I2, you see, initially it is not getting the dotted. You would say that I2 is leaving the dotted terminal. So, or for example, this is here, but this dot is here, but still then it would be subtractive because this is clockwise. So when it is entering, there is no dot. Ion is getting dot at the leaving point. So here it is entering, but that would be leaving. So in that case, that is also the minus, negative voltage. So therefore either or, for example, this on here and then this on there, then it's still the same thing.
So opposites add, same subtract.
Yeah. So this is entering at the dotted point. This is entering at the dotted point. Or both are leaving the dotted. For example, this dot is here. Think this dot is here and this dot is here as well. But then still current direction is the same. So you see, if this dot would be here, then ion is entering, but ion is leaving the dotted point. So this coil, which point has the dot, that is important, here or here. So, and then if this would be there, definitely I2 would be leaving the dotted. So if both are the leaving, then that is plus. Either both entering at the dotted terminal or both leaving the dotted terminal, then that would be the plus voltage for the mutual inductance. Otherwise, it is minus. I mean, same thing like algebra, plus plus multiplication plus, then minus minus multiplication plus, but then any of the plus minus gives you the minus result. Same thing as the algebra, similar. So therefore, as you understand this one, I hope everybody now understand. Can you calculate the V naught for this circuit? So therefore, what you have to do at the beginning, everybody, please write down two equations. Please write equation for left side loop for current ion and then write another equation including I2 for right side loop. And then you will see that how you can get the I2. And if you get the I2, then just multiply by 10. So therefore, result you can express in the polar format. For example, like the original voltage source. In that format, you can express V0, polar format. So at the beginning, everybody, can you write down two equation? What should be the equation for this loop? Apply the KVL, and here apply the KVL voltage law, including I2. Write down two equations, everybody, and then you see what you can do. So therefore, everybody see, just I'm giving you the hints. So this is my indicated direction, but this is minus plus. This is already given voltage source. But then here you can assume this is plus minus. Again, this is plus minus. So what you can write, this is source. So you can say like minus 145, then plus 4 plus J8, then multiplied by ion, and then plus J1 multiplied by I2. So mutual inductance with regard to the other current, this current, that will be the mutual voltage term. Everybody, could you follow me? So therefore, this voltage, that equals to ion multiplied by 4 plus J8, I mean in parenthesis 4 plus J8 multiplied by ion plus I2 multiplied by J1. That thing will be equal to 145. And then on the right side, you see there is no source like this. So that is fine. So 0 equal to 10 plus J5 I2 multiplied by ion J1. That will be the equation for this loop. So therefore, everybody, see, please you write down the very first line of the equation, and then you see what you can do. Everybody see? That is just I indicated that V0 will be 10 multiplied by I2. And then what I am doing, I am writing two equations for loop on left side. At that I said minus 145, that was the voltage source, plus ion 4 plus J8, and then Ji2, meaning that because this is 1, so I just write Ji2. That equal to 0, that is equation number 1. And then see the for loop 2, this loop, everybody see 10 plus J5 multiplied by I2, and then the mutual inductance, the mutual voltage due to this mutual reactance from the with respect to that current ion. So that's why J ion 0. This is equation number 2. Now from these two equations, what you have to do? You have to find out J2. That is your goal. And once you get the J2, and then you multiply it by R2, and then that will give you this result. So you should be getting 10 at an angle of minus on 35 degree. So everybody, can you please write down these two equations, and then you calculate, you try, and then see that you are getting the same result. Is everybody clear? Is it fine, or still you have confusion?
So the coupled induction,
Yeah,
is always in terms of always being multiplied by the other KVL. Like if
yeah,
you're doing
yeah.
I1, so J1 is going to be multiplied by I2.
Yeah. Because you see the mutual inductance is linking the other coil as well. So that's why mutual inductance is coming due to the other current. That is the meaning.
Okay.
Yeah. So therefore, for example, look the first equation. When I'm writing the first equation, first you take into account what is available here. So therefore, there is the source that minus 145, and then definitely there will be voltage drop here, voltage drop here. This is the self-inductance Ln on. This is L22, this is L on. So ion multiplied by, you see, 4 plus this one. And then you have to take into account this mutual inductance effect. This means because you are writing voltage equation, what should be the mutual voltage? that time this mutual reactance multiplied by the other current. That is the thing. The same thing when you are writing equation 2, this loop, first you consider the element which is available in this loop. So that's why first I2 multiplied by this 10 plus J5. And then again, this is the same mutual inductance, but it relate with that ion. So ion multiplied by that. That will be the mutual voltage for this loop. Julian, is this fine?
Yes, that's fine. I was originally doing like mesh subtracting I1 to I2, and that is wrong.
Oh, yeah. No, so therefore you see, no, not that one. So only you have to look this one. Because you see, this J, I mean, I understand that if it would be like normal loop, you see here there is no direct electrical connection. You look between J8 and J5. So therefore, when you do the normal circuit, not magnetically circuit, then you do that on ion minus I2. I understand what you are saying, yeah. So, but you see, there is no direct connection. They are connected through mutual inductance. That's why you are taking into effect the mutual inductance. Instead of doing that on that, you are saying ion minus I2. Because you see, ion current is flowing through this coil, I2 current is flowing through this coil. So there is some common linkage through the flux, through the magnetic field. There is some common link. That is this one. There is no electrical connection. Only they are connected through magnetically. That's why you cannot do ion minus I2.
That's clear now. Thank you.
Yeah, yes. Like J5 is its property, J8 is its property. But if you think about the other normal circuit that you have done so far, both DC circuit, AC circuit, there was, for example, one loop and one branch. In the same branch, for example, ion current is going downward and I2 was going upward, for example. Then that thing you are telling that would be correct. But you see, there is no electrical connection here. They are magnetically connected. And that magnetical connection is being established through that J1, not J8 and J5. That is the meaning. Okay, so have you all written down those two equations, equation 1 and 2? And then can you please calculate and can you make sure that you all get the 10 at an angle of minus 135? You just do at your pen and paper and then show me that you are getting the same result. So makes a practice. Oh, so everybody, so I think I mentioned last class. So you will be facing the midterm exam 2 next week. I mean, coming Wednesday, just a week away, September 21st.
Awesome.
So midterm exam 2, the syllabus will include this chapter, magnetically coupled circuit, and the previous 2 chapters, frequency response and application of Laplace transform to circuit problems. So the syllabus will include 3 chapters, Laplace chapter, frequency response, and this magnetically coupled circuit.
When did you say?
September 21st.
Wait, September?
Yeah, September 21st. This means next week. Today is, 14th. So
October, Dr. Ali.
October.
yeah. Sorry. sorry. Yeah. October. Yeah. Right. We are currently October, not September. October 21st. I'm sorry. Yeah. So
A week from today.
I am going to send out an email to everybody after the class. I will remind you. So if you see that at the beginning of the semester, I prepared that syllabus class schedule. I already uploaded and I discussed with you at the first class. So I am following that syllabus. So there I have scheduled October 21st, it is your second exam. And then I think sometimes, around November 10th, around, you will face the third midterm exam. I will remind you at least 1 week before. So therefore, no, what I am saying that in the midterm exam too, next week, October 21st, you will be facing similar problems. So that's why you all need to understand this problem and then solve. You will see very similar problem you will be asked in the exam. So then I think sometimes today you can see your homework 3 grade, homework 3, almost done. Currently I have locked that Dropbox where you submitted your homework 3. If you go eCourseware, you will see, no, you cannot see anything because I have locked it. Sometimes today I will open it and then you can see. And then in the next class on Friday, at the beginning, I will be discussing the solutions for homework 3. And I think today you have the deadline to submit the homework set 4, right? Yeah, and probably today, midnight. And then again that you can see the grade hopefully on Friday. So then you all are ready with the midterm exam. So are you trying this on, everybody? Has anybody got so far the result, V not?
Yes, I have.
And is it matching with this one?
Yes, I was able to type it into my calculator's matrix stuff and Gauss Jordan it, and that worked. So.
Okay. I mean, without doing these steps, I got it. Yeah, okay.
Yes.
Are we allowed to do that on the exam? Just put it into a matrix, or do we have to show the algebra and the work?
Whatever you do, matrix or algebra, you at least you have to write something. I mean, don't just write the last line. So, yeah.
Okay.
Yeah, if you directly write the last line, so then I am not sure that like you did yourself or you looked someone's or you texted or you emailed, because we are not seeing you in person, you see. So that's why at least you write either algebra or that matrix that you are doing, something you have to write. And definitely everybody, please first write down those 2 equations at first, because if you don't write those 2 equations correctly, and then still if you get the correct result, then that is surprising. So therefore, first you have to write the equations correctly, and then if your result is incorrect, then I will be assuming that somewhere you made mistake, either calculator or here. So then you will be getting the almost full credit. Now, on the other hand, if you did not write the equation in correctly, but still you are getting the accurate result, this means that is surprising. So then I would assume that you have looked someone or took some help. So you understand what I mean? Yeah. So therefore, so everybody, so at least you'll be writing those 2 equations and then so few steps, and then you get the result. So everybody, could you follow this algebra that I did? I just did it by hand and just by fully following the algebra.
Yes, you solved for I2 and equation 2.
Yeah.
Plugged in the values. Yeah, system of equations.
Yeah. And then I just substitute the value of I2 into equation 1, right? And then you see just algebra, normal multiplication, just Fedor algebra. And then I got the ion. But once I got the ion, but then I have to get the I2, because I have to determine the voltage V0, which is related to I2, not ion. So that's why, even though at first my calculation gave me ion, but I substitute the ion value again in that equation. This one, this is ion, and then multiplied by this number. So then I got I2 1.0 angle minus 135 degree. So then V0 is easy, just multiplied by 10, because the resistance value is 10. So is everybody fine? Could you follow this one? Or are you trying to
Hey,
do?
Doc, I think I got the same answer, but if you mouse up when you figured out I2 and you got I1 angled -90, I guess it doesn't matter, but I have I1 angled 270. I guess that's the same thing.
But ultimately, did you get V not this one?
Yes.
Okay, then fine, then fine, yeah.
Okay.
Then fine, yeah. Yeah, or sometimes somewhere you might consider the angle like anti-clockwise, then that might be different, but ultimately it should be the same thing. I mean, everybody, see, this is not difficult. It's just a matter of calculation. Either you do algebra, equation, or matrix, or using your calculator, whatever. As long as you are writing the equations correctly, those two equations, then you should be getting the same result. So if you have any mistakes here, then you would not be getting the accurate result, or there will be plus minus sign issue, etc. So is everybody fine?
Yes.
Yes.
Okay. Okay. So therefore, because this is already uploaded on eCoursera, this class lecture material, so you can see the calculation. But what I'm saying that instead of just looking, even though at home, everybody please make practice. So also, as I said, that sometimes even though you understand the problem fully correctly, but unless you do by pen and paper, so you may not get that result. So that's why everybody please make some practice. And you see, like this part sometimes take time, that consume your time, and that is the reason you need a long time in the exam. So you need to have some practice that how to do that, and then you will get clear idea, better understanding. Okay, so moving forward. So now we will be looking one concept which is called the transformer. So I think everybody, you know this term, right? The transformer. So transformer is actually the most efficient and most effective piece of electrical equipment. We call it electrical machine. So, and what is that? The transformer is the best example of the magnetically coupled circuits that we are discussing in this class. So transformer is the example of the where is the application of magnetically coupled circuits. That is the transformer. And you all know that this is called the heart of the system. Like, as you know, that how you get power at your home. So therefore, there is power plant. That power plant produces voltage or power, and then that is transmitted over the lines, and finally you get power at your home. But in between, there are lots of components between the power plant and your home. Transformer is one of that most vital. And I myself always say transformer is the heart. Like you have the heart in your body. If the heart is stopped, then you stopped. Similarly, if the transformer is out, then you will not get power at your home. So then what is the function of the transformer? Transformer, I have written here. Transformer is it transmit AC power to long distance. Transformer can step up or step down voltage. I am taking you to the board and I am explaining just at a high level idea at first. Transformer can step up or step down current, and transformer can isolate a circuit. So therefore, for example, everybody again, if you see this is one set of coil and this is other set of coil, there is no direct electrical connection. It is fully separated, fully isolated. But what is the function? It may happen that, for example, in this side you have 100 volt. In this side, by some arrangement, you can make the voltage double, triple, 3 times or you might decrease. You can make it half, you can make it 1/4. Similarly, current magnitude you can magnify it here or you can decrease. It depends upon the applications and necessity. So that's how you see transformer function, step up or step down voltage, step up or step down current, isolated circuit, and to transmit AC power to long distance. So therefore, what does that mean? And it is said AC power, not the DC power. So, and then everybody say, what is the definition of transformer? A transformer is a static device that transfers electrical energy from one circuit to another circuit through inductively coupled conductors, the transformer coil. This means the same principle as the magnetically coupled circuit. And as I said, it is the most efficient electrical machine. So it says electrical machine, that circuit, because I believe you all know a generator, there is motor, there are other device, electrical device, which we call machine. They all have the rotating parts. There is shaft and it rotates. So there is some rotational loss, friction loss, windage loss. But in this case, it is called most efficient because it is static. There is no rotational parts. There is no movement. I mean, there is only left side coil and right side coil. They are fixed. They are not moving. There is not shaft or rotating parts. So that's why it is the most efficient place. So therefore, when you will be going in energy conversion class, EEC 420 on course, I mean, at least those who are the electrical major, definitely you will be taking that course. Like we will be solving some problems. Always you will be noticing for transformer, efficiency is 98%, 99%, at least more than 95%. That's why it is called, it is the most efficient electrical machine. On the other hand, if you solve any problem about any motor, any generator, other device, efficiency like hardly you will get 80%, hardly 80%. In most cases below 80%. Because in motor generator, there is rotational parts. There is rotational losses, windage loss, friction loss, bearing loss. There are varieties of losses. But in transformer, only there is little resistive loss because that coil has some sort of resistance. So there, but at least there is no rotational loss. So that's why everybody, I mean, although we will be extensively discussing transformer in energy conversion class, but in this class, you all will remember that it is the most efficient piece of electrical equipment. So therefore, if any job interview or if any FE exam, if you are asked what is the most efficient piece of electrical equipment, you would boldly say that that is the transformer. And then why? Because this is a static device. It does not have any rotating parts. That's why. So now there are varieties of transformer like linear or nonlinear transformer, ideal transformer, auto transformer, even though there are other types. But in this class, I have narrowed it down. I will be discussing only these things, and that is enough for you at this level. And now let me take you to that whiteboard to understand the theory of that transformer. And then again, I am coming back to this slide. Hold on. Okay, so therefore we were looking at magnetically coupled circuit, and now we are looking at transformer. Everybody see. So transformer. Okay, let me before that let me draw a magnetic core material. Okay. Okay. You see, just I drew a magnetic material. It is called that magnetic material, or sometimes it is just called the core material. It is called. Now, on this magnetic material, I will be placing two sets of coil. This is on sets of coil, and this is other sets of coil. So can you see? So there is one set of coil on the left side. I mounted on the left side limb or arm of this magnetic material or core material, and on the right side. Therefore, as you can clearly see that there is no direct connection between this coil and then right side coil. So the left side coil, it is my primary. Here I will be applying the voltage VP, primary voltage. And in this side, we will develop the voltage. It is called the secondary side, accordingly the symbol. So secondary, this side is secondary and this side is called the primary. And instead of left side or right side or this circuit or that circuit, in engineering term, always it is called the primary. And this side is called the secondary circuit. That is the main. So I am discussing the transformer. Everybody say I am talking about the transformer. So how does this work? So we have two sets of coil on primary and secondary mounted on the same magnetic material. So what happens? First I applied the voltage on the primary side, which is VP. And keep in mind everybody, of course this is the AC voltage. We cannot apply the DC voltage on the transformer. I mean, I am answering that point why soon. First, let's everybody assume that this is the AC voltage VP. Once I apply the voltage VP, then current flowing through it, which I designated IP. Again, IP means primary current. And then you see that current is flowing through this coil. So what is the effect of flowing that current? That we learned before. So there will be flux. So the flux will produce, which is this one. For example, this is phi 1. And then this phi 1 will induce voltage on this coil, which is, let's designate by symbol EF, induced voltage. It is designated by symbol EF because of this flux. Because this flux is alternating in nature, because we have applied the AC current, so that flux is changing. This coil is static. This coil is not rotating or moving, just at a static position. But this flux, this is alternating. This means this is varying. So because this is varying and coil is static, consequently, there will be a voltage. That voltage is called induced voltage. So therefore, VP is the applied voltage and EP is called the induced voltage. Let me write down those terms on it. It is called the induced voltage. And then this is called, VP is called the applied voltage. So now, for example, this is the picture of an ideal transformer. Ideal transformer means I did not show any resistance. Everybody see, these are the coil. So you all know that coils means the inductance mainly. But in real practice, these coils have some resistance, very small value in the ohm range only, but they have some resistance. At this point, I am not putting any resistance. If I put any resistance, then that is called the real transformer. But right now I am discussing with you the ideal transformer. Therefore, I am not showing any resistance of these coils. So that's why, because there is no resistance, actually this VP voltage, that applied VP voltage will be equal to the induced voltage because there is no loss, no drop. Same voltage will be induced here or developed here. Okay, so I think everybody understand up to that. Then say our goal is that we have applied voltage VP. We want to see voltage here on the secondary side, even though there is no direct connection, there is no electrical connection. That is I'm trying to achieve. Now everybody see the sequence. I explained so far that because of the application of IP, it produces flux phi on this coil, and that induced voltage. Simultaneously, what will happen, because this is the magnetic material, you see, this is the magnetic material, or this is the core material, what will happen, there will be another flux that will start flowing through the core material. It will link the secondary coil and it will flow in that way. So therefore, that is actually that mutual flux that we have learned from the magnetically coupled circuit. So this means that initially there will be two flux. One is that phi that is just linked to this coil and it is moving around here, circulating around here. But because, I mean, it is the property of the magnetic material. If a magnetic material is excited, because you see, this coil is this coil is mounted on this body, on the magnetic core material. So this means that magnetic material got excited, core material got excited. So that's why gradually there will be electron flow, and that is causing that flux, which is that mutual flux. So therefore this mutual flux will move around. So this means this phi m, it is the common to both this coil and this coil. And phi is itself flux, or the leakage flux it is called. So now everybody see, because this phi m is here, it is linking this coil, and again the nature of that phi m is, it is alternating. This is the nature of phi m. But this coil is static. Consequently, there will be voltage built up on this coil, which is called the induced voltage on the secondary coil, E subscript S. Here we said E subscript P because primary side, this is E subscript S. And then because there is voltage, you might keep it open circuit, then there will be no current flow. But if you connect some sort of load here, whatever the load is, this is the load L. So then there will be current flow. That current name you can say this is IS, secondary current. Now even if you don't connect any load, but still there will be voltage available here. So the question is that how it developed the voltage. So therefore that you remember that previous class I was discussing with you that Faraday's law of electromagnetic induction, that in this case, everybody see the equation ES, that secondary induced voltage is proportionate to that d phi m by dt. You can say Faraday's law of electromagnetic induction, that if you have a coil and there is changing flux, because it is alternating in nature, it is AC flux, consequently it is changing with respect to time, then there will be voltage buildup. So now you can omit that sign, proportionality sign, and then if you put the equal sign there, so you have to put one factor, proportionality factor, which is NS. That NS is the number of turns of this coil, NS. Similarly, on the primary side, the number of turns are N phi. So as I was telling you, what is the meaning of that number of turns? Like this is one turn. Then if you twist, this is number 2. This is number 3. This is number 4. So that is the meaning of that N phi or NS. How many turns? So that's why this is the equation for this voltage. ES NS d phi m by dt. I mean, simply you take that E equal to N d phi by dt. Similarly, on the primary side, also you can relate with the similar equation, that for example, that EP, again that N d phi by dt. In that way, you can relate. I mean, the similar things, you can say right NP. Everybody, could you follow me so far?
Yes.
Yeah. And then, so therefore, this is first the voltage is transferred, voltage is built up. This means you are applying some voltage here. and then you will be getting some voltage here. Now, everybody say one thing. There is pretty interesting relationship. For example, this is equation number 1, and then this is equation number 2, for example. So therefore, if you divide like 1 divided by 2, then what you will be getting? You will be getting this type of relationship, like EP over ES. And then d phi t by d phi t will be cancelled, and then like NP over NS. So therefore, see the relationship. This is primary voltage, this is secondary voltage, this is primary number of turns, this is secondary number of turns. Now, for example, I applied 100 volt RMS on the primary side. And for example, on the left side, everybody just assume I have 10 number of turns. On the right side, this means NS, I have 100 number of turns. I put 10 times more. So therefore, what will be the secondary voltage? You will be getting 10 times. It will be 1000 volt here. Everybody look that equation. This is the equation. EP over S, NP over NS. And then I said your EP voltage, I mean VP means the EP. As I said you, that applied voltage equal to that induced voltage. I mean, you can equally use the symbol like VP, or you can use the symbol VS. It is the same meaning for ideal transformer because there is no resistance here. So therefore, whatever it is VP or EP, it is the same. But they are related to the number of turns. That number of turns is the governing factor to control the magnitude of the voltage applied at the primary side. So this equation is changing the amount of voltage on the right side. So therefore, everybody see this one. As I said that, for example, VP or EP is 100 volt. Just assume here and look the equation. And I said the NP value is 10, but NS value is 100. Then you see how much you are getting. You are getting 10 times higher voltage. This means here voltage is 100, but here you can get the 1000 volt. Everybody, could you follow me?
Yes.
Yeah. On the other hand, everybody see the example. For example, here on the primary side, your number of turns is 100. Now you change the value of NP 100. Keep the voltage value is the same. Your EP or VP is 100 here, but NP value is now 100, and this value is 10. You change this value. NS value is 10 just. You will be getting this time 10 times a small voltage. Only you will be getting 10 volt. It was 100 volt on the left side, but on the right side, you will be getting only 10 volt. Because your number of turns govern that one, control that one. Because 10 times is smaller, the number of turns, accordingly, exactly voltage will be 10 times lower. If it is 2 times lower, if it is like if you put 50 number of turns, you will be getting the 50 volt here, just half of that. Or if you put the equal number of turns, for example, here also you put the 100, your both side number of turns 100. If you apply 100 volt, exactly you will be getting the 100 volt. So this means your transformer can either increase voltage, decrease voltage, or can maintain the same voltage depending on the number of turns. So that's why the both sides voltage is related to the number of turns, how many turns you put there. Accordingly, current will be controlled. Current magnitude will be, as you are noticing, because voltage magnitude is changing, accordingly current magnitude will change. But current will be inversely proportional. If you increase the voltage here, then current will decrease. Here, if current is decreased, voltage will increase. Just the opposite thing will happen. So therefore, I am taking you to that slide now from this board. Everybody, could you follow so far?
Yes.
Okay, great. So now I'm taking you to that class page, then you will. So if that is the reason everybody say, what is the function of transformer? It can transmit AC power. Everybody say transformer is related to AC voltage only, AC power only. Keep in mind, it cannot transmit DC. So can you guess why it cannot transfer the DC? So therefore, if you just look that equation that I was explaining, see this one. I mean, this is the picture that I was explaining you. This is that core material. There is primary coil. These red color are the primary coil, and then blue color are the secondary coil. And that green color you see, the mutual flux phi, that is linking. So secondary winding, primary, exactly I explained you. Now everybody say that equation I was explaining, for example, that Vs, secondary voltage, Ns d phi by dt. Now you see d phi by dt, what is that meaning? Because phi is changing, it is alternating in nature, that's why d phi by dt. So now if you, everybody see, if you apply the DC voltage here, so then can you write this equation? No, because if you apply the DC voltage, flux will be produced, that is true, but that flux does not vary with time. You know that DC is independent of time, right? DC circuit is independent of time. Only AC circuit is the function of time, like V equal to Vm cosine of omega t. But in the DC circuit, it is the based on the DC voltage. It is time independent. So the DC voltage DC flux cannot vary with time. Consequently, because d phi by dt, for example, you applied 100 volt DC and then it produces 10 Weber flux, but then d10 by dt, that will be 0. Consequently, your voltage will be 0. So therefore, everybody keep in mind, if you can apply DC voltage, but it will not do anything on the secondary. Straightforward, you will be getting 0 voltage, 0 current. But there will be some problem with that, because you are not getting anything, but still you are applying DC voltage. This core magnetic material will be saturated, and gradually it might be heated up. It might be burnt out. So that's why, I mean, you should not try to apply the DC voltage on the transformer. Everybody, do you understand what I'm saying?
Yes.
Yes. So therefore, keep in mind, I mean, this is also the, the FA exam question, that why the transformer cannot transfer DC power.
Because DC is not measured by time.
Yeah, because DC does not have time varying quantity. DC is fixed. Therefore, this equation is the principle, or the bottom equation. This is for the primary side. Look at the primary side, forget about the secondary side. Think only about this one. If you look this equation, d phi by dt will be 0 for DC. Because you know that what is the time derivative of a constant number? It is 0. So that's why you cannot apply the Faraday's law of electromagnetic induction when it is DC. That's why you cannot transfer. I mean, even though you apply, but still, if you use a voltmeter, you will get the 0 reading, both for ammeter, voltmeter. Then the negative sequence, adverse impact will be, if you put your hand on this body, gradually it will be heated up because of that flux. So that is the property of magnetic material, because it is getting some sort of current, even though it's steady or the constant voltage, constant flux, but gradually it will be heated up. So that's why it is not recommended or not advisable to apply the DC on the transformer. So, and everybody now you can understand, when we are applying the AC voltage, only then it can increase or decrease the voltage that we discussed on the board. And I have written down that equation here again, you see. Vs over Vp is Ns over Np, that I was showing you. Now, because we are applying DC, it cannot do anything on the secondary. That is the reason you cannot transmit DC power over the long distance. everybody come back to this first point. What is the function of transformer? To transmit AC power to long distance. What does that mean? For example, you have a power plant and you have your home. So the distance between your home and that power plant could be several hundred miles. For example, 500 miles, even 1,000 miles. So therefore, for example, if you produce just, what is your voltage at home? Phase to neutral. What is the voltage at home?
120.
120. Now everybody think, what is, I am asking you all a question. For example, I need at my home 120 volt and my power plant is 1,000 miles away. Therefore, will you produce 120 volt there to get the 120 at home, or you need much more higher voltage there?
Depending on the source, you'd step it down or step it up.
Yeah, therefore everybody say, if you just produced 120 volt at the power plant, and if it is 1,000 miles away, on the way, maybe only after 100 miles, the voltage will be zero. Never ever it can reach your home. The reason is that there are coils. I mean, power transmission, these lines means there are cables, and those cables have resistance, inductance, some capacitance. There will be voltage drop gradually, right? So therefore, ultimately, you will be even getting the negative voltage at home. That is the reason, first in a power plant, voltage is produced at a reasonable amount, not 120, some higher number. And then because on the way there will be voltage drop, consequently, you need to put this device, transformer. You put transformer. And then, for example, here it is your power plant. Immediately after that, you put a transformer and then step up the voltage to very high level, very high value. Like in United States, we have up to 750 kV. Okay, so can you imagine? 750,000 voltage. And then again, you put other transformer gradually, you step down, step down, step down, and finally you get 120 volt at your home. So this means, because I am assuming just an example, that the distance between your home and then power plant could be 1,000 miles. Even there are examples much more than that, at least several hundred miles. So therefore, on the way, there will be huge voltage drop. That's why you need these devices. Now,
Well,
okay.
I'm sorry. Will flux be given, or are we going to have to do that double integral for that?
No, that is the integral, because the circuit will be connected through the cable.
Okay, so
You see, for example, this is the secondary. That assume that the primary side is a power plant, okay? And then that power plant is connected these 2 points. This is the secondary. As I said, this is the load side. Then you take the long cable. You connect here several hundred miles cable. And then after several hundred miles, again you put another step down transformer. Again put after several miles step down transformer. So therefore, I think you all know that time to time you had during the summer, very peak period, the transformer got disconnected, like transformer out. Even though in the University of Memphis area, sometimes that happen. I mean, those who live in the dormitory, I think you have faced that issue. Many times that happen, or at least once every year. So because transformer got overloaded, during summer, most of the people starts using their air conditioning system. But typically it happens around noon or the early afternoon. It is overloaded and then transformer got disconnected. So that's why I said that, and that if the transformer is disconnected, then like the connected loads will be under dark. They will not get the power. So what I was explaining, so everybody see, if you apply the DC, then it cannot do anything. But what I am saying that when we are, I mean, in this class, we are discussing the AC, this is AC circuit. Isn't the AC circuit complicated than the DC circuit? Because AC circuit has inductance, capacitance, phase angle, frequency response, and magnetic. It is really, I mean, complicated than the DC. because DC has only that voltage source and the resistance. And if it would be the DC, then our life would be much more easier. We did not do calculation for phasor or phase angle or impedance or anything, reactance, admittance. My life would be much more easier. But then what is the motivation to go with the AC? This is the motivation. Motivation is that because at your home, to get the power, you need the transformer along the way, along the line, because it can step up, step down. DC cannot do anything. That is the reason to explore the AC. That is the philosophy behind using the AC power. Everybody, do you understand what I'm saying?
Yes.
Yes.
Yeah.
I mean, doesn't the question come in your mind that why I will deal with the AC? Why not the DC? Because DC is much easier. Everybody think that your circuit analysis on it was much easier. It was than the AC, because AC is getting. But why then we are using that thing? That thing I am answering to you, because you need transformer along the way to get power at your home, and you cannot use the DC. That is the meaning of this sentence, the first bullet. What is the function? To transmit AC power to long distance, meaning that you can transmit DC power to long distance. I mean, for a short distance at your home, for maybe a small several meters, you can send some DC power, that is okay. I mean, in real practice, it has been up to 20 miles or 30 miles, you can transmit DC power, I mean, without transformer. But after that, gradually there will be voltage drop. Ultimately, you cannot do anything. And then transformer does not work on the DC. That's why the power engineers have explored the AC. And once I am coming the AC, then that question is coming, what is the phase angle? How I will calculate that? And then impedance, reactance, admittance, everything is coming. But still with those things I am fine, because I am getting power at my home. I want to get benefit from that power. That is the motivation of that AC power. Okay, so therefore everybody hold until that. I mean, I think you have the other classes soon. So we produced the voltage at this point, and next class I will be discussing about the current and followed by 1 or 2 numerical example, and then everybody will be fine about the transformer. And then, as I said, once you will go to that, at least those who are the electrical major or those who have the dual major, you must come to that energy conversion class, EEC 4201, and then we will be spending at least 5-6 classes on the transformer. There are lots of phenomenon and theory and problems about transformer. Okay, so does anybody have any questions, comment?
I have a question, kind of off topic, maybe off topic. What is the contribution to the flux from the transformer core? What I mean by that is, like, when you take a wireless induction charging, like a wireless charger, there's no core.
Okay, so in this case, for example, the flux, as you can see, like this is, its contribution is that this is flowing from here, from primary side to the secondary side through this magnetic material. Now, just now you said about that wireless charging. In the wireless charging, what will happen? Just a second, just a moment. Let me. I will just draw a big thing. So I understand your question. Transformer.
Sorry, everybody.
No. So you are fully fine. Let me draw. So today I drew that picture that I discussed. This is also the example of transformer. This means, you see, in this case, this is magnetic material, this one. And then you put the primary coil. This is also the separate magnetic material. You see, in the previous picture, it was a common magnetic material.
Right, so when it's connected, I can only assume that the flux will be greater.
Yeah. But in this case also, what will happen, once you apply the current, there will be flux. There will be another flux. Something is going here, and from here something will come here. It is just the air. There is nothing between. Still inside with the air, there can be the mutual flux. So that is the contour. So without that flux, there will not be any voltage on this coil. So there is self flux phi 1, there is self flux here phi 2, but there is phi 1 too, even though there the magnetic core material is separated. So therefore air is working as the media. So that is the function of the flux. Now it depends on this distance. If the distance between this core material is too far, then there will be nothing happening on the secondary coil. So therefore, the point that you mentioned, that car charging, it depends on the distance. How far wirelessly it can be charged? Maybe up
Yeah,
to,
I'm just asking this for the project.
yeah. So maybe up to only several meter it can charge so far. So far, according to the latest technology, maybe only 2 meter or 3 meter distance it can cover. Beyond that, you cannot charge.
All right, thanks.
It depends on the distance. Therefore, really, it should be within reasonable distance. If it is too far, but the currently research is going on that how we can transfer, the charge car wirelessly when the car is running. You see, pretty interesting. You are running your car, you are driving your car, and if there is charging station nearby, automatically, dynamically, it will be charged. But then the distance will be huge, not just 1 or 2 meter, maybe 1 mile or a half mile. That research is also going on. It's still not realized. It is just being explored. Maybe in next 5 years, 10 years, you can see that.
That'd be pretty sick.
Sorry?
Wireless power is the future.
Yeah. That is coming. Wireless car charging, that is huge. I mean, huge topic. We can even from one car, you can charge the another car. For example, you took charge from a power station nearby while the car is moving, and then you can lend your charge to someone, to your friend's car. I mean, all the pretty interesting concept is coming. Maybe in next 10 years, you can see many things. And most of our car will be changed to the electric car, or at least the hybrid car. So the many things are upcoming.
Be careful, Dark Ollie. You don't want those oil companies coming for you.
Yeah. Okay. So, is there any other? I think many of you have next class. Those who have classes, please, you can leave. I think already it is late. Is there any other questions, comment?
No, that's for me. Thanks a lot, Doc.
Okay. Okay.